Hey everyone, welcome to this explainer. I'm absolutely thrilled you're here today because we're looking at something that is quite literally driving the entire future of technology. For decades when we thought about computer chips, we mostly just thought about the silicone brains inside, right? The packaging, that little black square you'd see on a motherboard, was honestly just an afterthought. It was just a protective shell. But wow, not anymore. Today, packaging is the crucial, absolute hero of the AI revolution.
So, why does AI desperately need advanced packaging? To answer this, I'm going to ask you to completely rethink what you know about semiconductor manufacturing. We're all super used to the idea that chips just get smaller, faster, and more powerful every single year, like clockwork. But right now, the titans of the tech world are literally hitting physical walls. The math and the physics are forcing a massive change, and the only way out is through totally revolutionizing how we package these tiny electronic brains together.
Okay, let's dive into this history to see how we got here. For the past 40 years, traditional packaging was basically just a high-stakes race to squeeze more connection points into smaller spaces. Back in the 1980s, we had DIP, those chips with the metal legs on just two sides. But as chips got smarter, two sides just weren't enough. So the 1990s gave us QFP, which put pins on all four sides. Then, mobile phones demanded thinner devices, because obviously nobody wanted to carry around a brick the size of their head anymore, right? So the 2000s brought QFN, tucking those connections neatly underneath the edges. Finally, when big CPUs needed massive data, we couldn't just use the edges at all anymore, so the 2010s popularized BGA, turning the whole bottom of the chip into a grid of tiny solder balls. But as you'll see in just a second, for the AI era, even this full bottom grid just isn't going to cut it.
So here's the roadmap for our explainer today. We'll start with 1, the AI hardware bottleneck. Then 2, breaking the memory wall. 3, the 2.5D horizontal highway. 4, the B200 evolution. 5, stacking up, 3D packaging. And finally 6, redefining the chip boundary. Let's get right into it. Section 1, the AI hardware bottleneck. Let's talk about the physical limits of chips. Let's start with our first major challenge here. We're going to look at the absolute physical limits of modern chip manufacturing and why the old playbook of, just making a bigger chip is completely off the table. Consider the size of today's processors. Nvidia's flagship AI chip, the H100 GPU, measures 814 square millimeters. Now, why does that matter? Well, because the absolute maximum size that today's advanced lithography machines can physically print, which is known as the reticle limit, is 858 square millimeters. So the H100 is perilously close to the absolute maximum possible size you can physically manufacture on a single piece of silicon. AI obviously demands more computing power, which usually means a bigger chip, but we literally cannot make a single chip any bigger than this. And that size limitation introduces a massive dual threat. You see, an AI GPU is an absolute processing monster, but its raw speed creates this huge problem known as the memory wall. Think about it like having the fastest, most expensive factory in the world, but your raw materials are being delivered by bicycles. The GPU finishes its calculations so incredibly fast that it just ends up sitting there completely idle, starving and waiting for the next batch of data to arrive from the system's memory. And for cloud providers spending millions on these chips, idle time is simply unacceptable. No way. Which brings us to Section 2, breaking the memory wall by moving memory closer. So, if the chip can't get bigger and the data is moving way too slowly, what do? Well, you have to completely rethink the architecture. You break that memory wall by fundamentally moving the memory itself. And this concept brilliantly illustrates exactly how engineers solve the data starvation problem. Instead of fetching data from standard memory modules that are far away on the motherboard, they introduced high bandwidth memory, or HBM. They took the memory and physically moved it right next to the GPU, on the exact same package. It is literally like building a massive multi-story 3D warehouse right next to your high-speed factory. The data doesn't have to travel across a slow motherboard anymore. It just shoots over to the GPU instantly through these ultra-wide, super short pathways. Moving on to Section 3, the 2.5D horizontal highway, connecting at high speed. But moving the warehouse right next to the factory creates an entirely new engineering nightmare. How do you build roads fast enough and wide enough to actually connect them? Well, this brings us to the massive architectural leap of 2.5D packaging. To connect the GPU and the HBM at lightning speeds, you need wiring that is unimaginably dense. Traditional organic circuit boards, the classic green boards you're probably used to seeing, they just cannot handle the submicron wiring required here. So the industry created the silicon interposer. This is essentially a microscopic, ultra-precise circuit board made out of actual silicon. And because it's made of silicon, it can be manufactured with the exact same microscopic precision as the chips themselves, which allows for tens of thousands of data lanes to run between the memory and the processor. Let's walk through exactly how this all comes together in TSMC's famous CoWoS architecture, which, by the way, stands for chip on wafer on substrate. Okay, step 1, the GPU and HBM chips use tiny microbumps to connect face down right onto the silicon interposer. Step 2, the interposer then acts as this hyper-fast horizontal highway, routing massive amounts of data back and forth between the chips. Step 3, to get power and data from the outside world through silicon vias, or TSVs, drop connections vertically straight down through the interposer. And finally, step 4, standard BGA solder balls at the very bottom connect this whole super package to your main computer motherboard. It is an absolute masterpiece of physical engineering, for sure.
All right, Section 4, the B200 evolution, pushing beyond reticle limits. But as amazing as that H100 package is, the relentless pace of AI meant it really wasn't going to be enough for long. We have to pivot to the next generation and look at how this tech had to evolve for those giant AI models. Now, what's really interesting here is how the B200 outright cheats physics. Remember the reticle limit we just talked about, the maximum size of a single chip? Well, the H100 pushed right up against it. So for the B200, Nvidia didn't even try to make a single bigger chip. Instead, they took 2 maximum-sized GPU dies and stitched them perfectly together to act as one single monstrous brain. This jumps the transistor count from 80 billion up to an astonishing 208 billion, and massively increases both memory capacity and bandwidth.
But here's the catch. Stitching 2 massive chips together totally broke the previous packaging method. You see, the CoWoS method used for the H100 relies on one single continuous block of pure silicon for its interposer. If you try to make a pure silicon interposer big enough to hold 2 maximum-sized GPUs plus all their memory, well, it becomes incredibly expensive and highly prone to cracking and breaking. The solution? CoWoS-L. Instead of a massive silicon slab, it uses standard, cheaper organic materials for the main base and only embeds tiny, highly precise silicon bridges exactly where the heavy data traffic flows between the chips. It's a brilliant, really flexible compromise. Which leads us to Section 5, stacking up, 3D packaging. Building upward. So we've seen how engineers expand horizontally to break the chip size limit, right? But there's a second pillar to advanced packaging. When you run out of room side to side, you have to build upward. This is where 3D packaging comes in, and the absolute star of the show here is the TSV, or through silicon via. When you look at an HBM memory module, it's not actually one chip. It's a stack of several memory chips, literally piled up like pancakes. But data doesn't clumsily route around the outside edges of these chips. Instead, engineers punch vertical, microscopic data channels directly through the silicon of every single layer. It works exactly like a high-speed elevator shaft, running straight through the center of a skyscraper, allowing data to instantly shoot up and down the stack. And because we can stack chips like this, the capacity gains are just incredible. The older H100 featured high-bandwidth memory stacked 8 layers deep. The newer B200 pushes that to 12 layers. Think about that for a second. They increased the memory capacity by 50% without taking up a single extra millimeter of space on the horizontal circuit board. Why does doing this in a microscopic footprint matter so much? Because in massive, power-hungry data centers, every millimeter of physical space and every single drop of energy saved translates to millions of dollars in a vastly smaller environmental footprint. The industry is already moving towards 16 layers and beyond, packing absolutely absurd amounts of storage into these vertical marvels. So the crucial point here is that advanced packaging relies on 2 distinct, brilliant strategies working perfectly in harmony. First, you have 2.5D packaging, which is your horizontal expansion, stitching multiple chips side by side to completely shatter the illusion of a maximum chip size. And second, you have 3D packaging, which is vertical expansion, stacking chips straight up to squeeze absolutely every ounce of performance out of a tiny square of physical real estate. And finally, Section 6. Redefining the chip boundary. Let's look at the supply chain shift. We've looked at all the technical marvels, but let's take a step back for a minute. These incredible physical feats aren't just cool science experiments, they are completely rewriting the rules of the entire global semiconductor industry. Because this process is so intricate, the supply chain has totally shifted. You can't just design a chip and then figure out the packaging later. If you're designing an AI chip today, you are locked into a specific foundry's packaging ecosystem, like TSMC's CoWoS, from your very first blueprint. Because of this, foundries have basically seized the highest value, most complex packaging steps. Meanwhile, traditional packaging companies, known as OSATs, they're adapting by handling the overflow, the testing, and the mature technologies. The line of what even constitutes a single chip has literally been erased. A GPU today is just a beautifully orchestrated symphony of dozens of chips acting as one. Which leaves us with this massive industry-defining question. With chips pushing the boundaries, getting infinitely wider on organic substrates and stacking taller with microvias, where does the real value in the supply chain lie next? Who is going to provide the ultra-pure materials, the high-precision testing equipment, and the microscopic assembly arms of tomorrow? The physical engineering we've explored today is nothing short of breathtaking, but the financial and strategic battles over who controls these packaging technologies, well, they've only just begun. Keep this in mind the next time you hear about a new AI chip. The real magic isn't just the silicon, it's how they put all the pieces together. Thanks for joining me on this explainer, and keep learning.